Today, we are stepping into the virtual physics lab. Our mission? It's all about measuring a wire's resistance, and we're going to use one of the most fundamental principles in all of electricity to do it. Let's jump right in.
So how do you even do that? I mean, electrical resistance, it's this core property that controls how easily current can flow through something. But you can't see it, you can't touch it. Well, turns out, with the right tools and a really brilliant piece of physics, you can measure it with incredible precision. And that's exactly what we're going to do today.
So here's our game plan. We'll start with the goal, we'll cover the core principle behind it all, then we'll build the circuit, take our readings, crunch the numbers, and finally get our result. The whole shebang from start to finish. Okay, first up, the goal. Before we start connecting any wires, we have to know exactly what we're trying to achieve. You know, every good experiment has to start with a really clear mission. So our aim is to figure out the resistance per centimeter of a specific wire. But listen, we're not just hunting for a single number. The real key to this experiment is plotting a graph of voltage versus current. That graph, that's what's going to visually reveal the wire's hidden properties. All right, let's talk about the core principle that makes this whole thing possible. It's a name I guarantee you've heard before, Ohm's law. To put it simply, Ohm's law tells us there's this direct, totally predictable relationship between voltage and current. You crank up the voltage and the current increases right in lockstep with it. That proportional relationship is the little piece of magic we're about to see for ourselves. And this is the super elegant formula that sums it all up. V equals I times R. V is for potential difference, your voltage, I is for current, and R, well, R is that invisible property we're hunting for, resistance, measured in ohms. With the theory locked in, it's time to get our hands dirty, virtually of course. Let's build this circuit.
So here's all the gear we're going to need. We've got a resistance wire, a power source, a voltmeter for voltage, an ammeter for current, but check this out, the rheostat. This is basically a variable resistor, and it's our secret weapon. It lets us change the current flowing in the circuit so we can get a whole bunch of different data points. Now, let's see how it all plugs together. Where we put our meters is absolutely crucial. The ammeter you'll see is connected in series. That means the current has to flow through it to get measured. The voltmeter, on the other hand, is connected in parallel, across the wire, to measure the voltage drop. You gotta get this set up right, or the readings won't mean a thing. All right, our circuit is built. Now let's walk through the actual procedure. How do we collect the data we need? The process is pretty straightforward. First, and this is important, we clean the wire ends with a bit of sandpaper. Why? Because even a tiny invisible layer of oxidation can add extra resistance and totally throw off our results. Clean connections are key. Okay, so with the circuit built, we check our meters and then we get to the fun part. We use the rheostat to set a current and we write down the readings from both the ammeter and voltmeter. Then we do it again and again. Taking multiple readings like this isn't just about being thorough. It helps us build a reliable dataset that really shows the true relationship between voltage and current, and it smooths out any little errors from a single measurement. We've done the hands-on work, now for the payoff. Let's look at the data and see what story it tells us. Okay, so here are 5 sets of readings taken straight from a lab manual. Check out the ammeter and voltmeter columns. As one goes down, the other follows. But the really interesting column is that last one, R equals V divided by I. Look at how, despite some tiny variations, the value stays incredibly consistent, right around 1.56 ohms. That, right there, is Ohm's law in action. And when we plot that data, voltage on the y-axis, current on the x-axis, we get this, a perfect straight line going right through the origin. This graph is the visual proof we've been looking for. It confirms, without a doubt, that the relationship between voltage and current is linear, which is exactly what Ohm's law predicted. The slope of this very line is what gives us the resistance. So, we've confirmed the principle. Now it's time for the final act. Let's calculate the specific value we set out to find from the very beginning. So, from the slope of our graph and the average of our V over I calculations, we get a mean resistance for the entire wire, and that value comes out to 1.56 ohms. But wait, remember, that's the resistance for the whole wire. Our original goal was to find the resistance per centimeter, so we need one last piece of the puzzle, the wire's length, which in this case is 28 centimeters. The final calculation from here is super simple. We just take our total resistance and divide it by the total length of the wire. And boom! There's our final result.
The resistance per centimeter of our wire is 0.0557 ohms. We did it. We successfully measured a fundamental property of this material.
So if there's one thing to take away, it's this. By carefully measuring voltage and current, we didn't just find a number. That consistent ratio we saw on the table and that beautiful straight line graph, they both gave us powerful evidence that beautifully verifies a fundamental law of physics.
This whole experiment just peels back the curtain on the hidden electrical properties of a simple wire. It really makes you wonder, doesn't it? What other invisible, fundamental properties of our universe are just out there waiting to be uncovered with a clever experiment and just a little bit of curiosity?